Thank you. All right, so I'll tell you a little, and I hope a lot of this will be fairly technical, but hopefully I'll be able to make it clear enough for you to see where I'm headed with it. I like this, my current favourite definition of epilepsy, because you can define it in lots of ways, and this is from a pretty old article in an obscure journal, but I thought it sums it up really well. A state of continuing dread, punctuated by periods of disturbed behaviour. So I think that sort of tells a story, like we just heard, about what the situation is for people in the real world. And so I've always been interested in systems that we might be able to use for seizure prediction, because so much of the burden is through the unpredictability of events. And we have this problem where we've got lots of new treatments and things, and they're great, and there's been huge advances and so on, but we're still stuck with this problem that a lot of people aren't well enough controlled. But the big disruption for them comes because they don't know when the events are going to happen. And if they knew that, I always thought that would solve part of the problem. Just to mention, I've got some vested interests here because I'm very involved in EpiMinder and CM Medical, but we'll come back to why that's relevant. So here we go, and this was written in the 40s. In the murkiness of present-day ignorance, superstition and fear, epilepsy for the sufferer may be defined as a state of continuing dread interrupted by recurring attacks of involuntary behaviour. The behaviour may be associated temporarily, to be sure, with mental or physical disturbances, or both. I think that's about the best definition you could have. So why do we need seizure prediction? Well, I think to give people back their independence primarily. And, as we've just discussed, the unpredictability is such a big component of the restriction. Personal safety, working on a roof as a plumber. I mean, it's amazing how often you come across this situation. Truck driving, working at heights, working around water. The driving issues and work are such big problems, and it's terribly stigmatising. And knowledge of when you might get into trouble or have an event would save so much stress for people. As well, if we could predict seizures better and understand them, we might be able to do a better job of stopping and starting the treatments that we have, and figure out what the new ones are actually doing, because a big problem is that it takes so long to figure out what a new tablet does. Nowadays, there are new treatments for epilepsy that involve direct stimulation of brain and direct delivery of drugs to brain, and it might be that we could control these systems with ways of understanding when seizures were going to happen so that they could deliver the treatments only when they were needed. When I talk to people who aren't in the area about why is this a problem, and surely people know when they're having seizures and that, I'll show you a couple of videos. So this is, maybe I won't. Is it playing there? Oh, here we go. So the lady on the left is with her sisters there in the kitchen, and they all know what to look for. So she's being monitored. You can see she's got a device on. You can see on the EEG in the background, the seizure starts there. You just see her slump slightly there, just there. And she stops cutting the celery. Not completely. She's not completely out of it, but no one notices. So she's with people who know what to look for, who know what the seizures are like. It's broad daylight. They're standing around talking, doing things, but no one sees this seizure going on. So this is a big problem, that patients having a lot of seizures they don't know about. And we know through our work in the home monitoring situation that 64% of the events we record are not noted by the patient or those around them. So it's a lot of events. Then when, you go to Centrelink or whatever and say the seizures are a problem, and they go, well, why is blanking out for a few seconds a big problem? Why does that stop you doing anything? I say, well, it's a bit more than that. And this is a bit confronting, this video. So, but I think, usually I like to show to people who are not involved in epilepsy so they understand what the problem is. So this same lady, kitchens are dangerous places, right? Sharp surfaces, pointy edges. And see, she just slumps there again slightly. And then the head turning as this more significant seizure happens. And you can understand the consequences of all of this. And I don't really need to show that to an audience like this, but for other people who don't understand what this really means at home and when you're having seizures, it's very powerful information. So we started doing seizure prediction from a theoretical point of view, and then we became involved with a company called Neurovista over 10 years ago now, who had a system that we could implant inside people's head to record their EEG continuously and predict seizures. Well, that was the aim. We didn't know whether we could do it. But that was very novel. The work we'd done before that suggested that we could predict seizures, but that it was impossible because you could never connect enough EEG data to do it. So this device came along, and the big thing up the top there with the wire, and that's the charger. The black box is what the patient carried, and it showed a series of lights that told them whether a seizure was going to happen in the hours ahead. And that pacemaker-sized box and the electrodes are what were actually implanted in the patient. So it was under the collarbone, just like a heart pacemaker with electrodes going into the head. And it was amazing because we got, EEG over very long times. We'd only ever recorded EEG from people for a couple of weeks at most, ever before from inside the head. But here we had people walking around doing their day-to-day stuff with this thing being recorded. It was a big deal to do. We had to put a big hole in the head. You can see in the top right there, and there's a bump on the chest in this pretty thin guy who, you've got a pacemaker-sized thing like that. They're pretty obvious. And I won't go through all of the study, but we could predict seizures with it. So this is these are graphs for the various individual patients that we did the prediction in, where we had enough data, and we were able to predict the seizures on average about 90 minutes before they happened. Anywhere between 8 minutes and 4 hours. So it actually worked, but it was a great deal of trouble to do. And unfortunately, the company who were out of America who'd made it couldn't get people interested enough. So investors who you need to do this sort of stuff thought that this was kind of crazy, and no one had ever agreed to have it done.
Excuse me, was that 19 or 90 minutes?
90, the average warning? 90. 90. Yep. So it's not bad. So the company collapsed, but we did learn a lot from it, and we'll come back to how it was very important. But we also found out lots of other things. So this is the graph of the seizures for an individual patient. So the patient was reporting before they came into the study having 17 seizures. They're actually having 13 seizures that we could see. They were probably having another couple where we could just see the electrical change, but we didn't know for sure they were having a seizure with it. And we recorded a lot of other electrical changes which probably weren't important. But other patients had this, where they were reporting about 5 seizures a month, actually having one every couple of months at best, not having anything that that we could see on the EEG that they weren't aware of, but reporting an enormous number of events that weren't seizures. So this is a big problem too, as it turns out. People are interpreting a lot of their things as seizures, and we see all this again now in the home monitoring thing. People having events, they say they're having an event, you look at it, so you're not having a seizure. And sometimes they convince themselves they've had a seizure, and even those around them are sure they've had a seizure. So we've got this problem that you don't know when people are having seizures, and they don't know when they're having seizures, and sometimes they think they are when they aren't. Because people interpret all sorts of symptoms as maybe being related to their seizures, and you think, did I forget something that I was just doing, or was that a seizure? So it's hard. But we could see these other funny things in the activity. The blue lines there, just all the electrical activity in the brain, and you can see that it's going up and down. This is measured over many days. So this seizure activity, we can see these funny patterns. The red lines when seizures are actually happening. So you can see seizures are actually happening at particular times when this activity is coming in waves. So this was an important thing that we learned. And when we looked over the course of a day, so I've got my autopilot pointer there so that I didn't need to use it. You can see there are times of the day when seizures just don't happen. Those little coloured dots are all the seizures happening. And down the bottom there's a 24-hour clock. There are parts of day seizures happening, and there are other parts of day seizures that are very prone to happen. A lot of people would tell you this, a lot of patients would tell you that seizures happen at particular times of day. And most clinicians probably didn't spend enough attention thinking about it, because people would say, their partner would say, I reckon he always has them about between 3 or 4 o'clock on a Monday afternoon. You think, oh yeah, sure, probably that's just when they're with them. But in fact, it was true. And so there are not only these patterns across the course of a day, but patterns over a week and months and probably seasons and probably decades, but we don't have decades of data yet. We were able to take this sort of information and through complicated systems extract these cycles of activity for people. So don't worry about all the details here. These are just individual patients, but these are just their individual cycles. So this patient has cycles that run between 1 hour and 1.5 days. Here's one who had cycles between 3 and 40 days and so on. So everyone's cycle was different. There were some similarities, and there were some very powerful cycles that we find frequently, but everyone's different. We can take that out, so we can use sophisticated mathematical techniques to take that information out and see in circadian, so these daily cycles, so the purple colouring to the dots there tells you these are statistically significant cycles. They're very powerful cycles for a patient there. But you can see in the next bit that there are multi-day cycles. So again, the purple bits tell you when these are important statistically. So you can see very strong cycles out over many weeks for that individual. So this is critical information. And when you plot out the information that we were getting electrically from these implanted recorders in people's heads, so the bars there, the dark grey bars, that shows you the seizure activity. So how many spikes of seizure activity they're having in an hour. And that's spread over, days or weeks or whatever, 7 days in this case. And you can see the red dots represent when seizures are actually happening, or at least ones that the person knows about. If we zoom out a little bit though, and look over many weeks, you can see there's a bit of a pattern to it. And it's a complicated pattern, but you can see there's a pattern to the seizure activity. If you zoom out even further, you can see that these complex patterns and the red dots of when seizures are happening have got kind of a predictability to them. The pattern and the curve of that graph might not be completely regular, but the red dots when the seizures are happening have got a particular relationship to it, so that's really important. So these cycles where seizures are patterned over many days, weeks and months turn out to be important. There was a lot of skepticism about them when we first observed them because people thought that we were causing them just by the time of the day we were giving the tablets, and the tablets were affecting the electrical activity and so on. But that's obviously not true. And we see this in animals too, so that studies have been done showing in animals with epilepsy that you see the same patterns and they're not treated and so on. We can take this sort of information out for individual patients and figure out what are their daily cycles. So here showing you that for the patients, the dots of when the seizures happen there are scattered all over, but when you analyse them and you use these statistical techniques to figure out when they're going to happen, you can see there's a daily cycle for this patient where events are occurring at certain times between 8 a.m. and 8 p.m. But there's a weekly cycle where they're very much more likely to happen on Monday, a bit more likely to happen on Saturday. And a monthly cycle where in certain weeks of the month they're more likely to occur. And a lot of you will be thinking to yourselves, I know exactly what you're talking about. It turns out most people have cycles that we can find. Most people have a cycle. 86% have at least one cycle. The stronger cycle is a daily cycle. And a lot of seizures are linked to waking or sleeping or particular phases of the sleep-wake cycle. But there are lots of other cycles, and patients have these cycles extending over many weeks. And a very common one is around about 28 days. And of course, if that's in women, they relate it to their cycle. But strange enough, men have exactly the same cycles. It's just they don't spot them. See, women have got something to link it to. But men don't notice that they've got a 4-week cycle until you point it out to them generally. So that's interesting. And others since then have gone on and shown that, looking at other kinds of devices that are implanted to record the brain's electrical activity continuously, showing these cycles exist. And as I mentioned, shown them in animals like rats and so on as well. And they've been shown to exist in dogs. So these same cycles of activity occur. So one way of predicting or forecasting seizures was to take information out of the EEG that was like a signature of when a seizure was going to happen. And that's what we did with that first study. We had the electrodes in your brain, we recorded the seizure activity, and we spotted things that were happening in the trace before a seizure happened, a signature that a seizure was on its way. But we could see that there was another way of doing it, and that we could figure out when these patterns of seizures were occurring and what the pattern was for an individual, and we could build a prediction for them based on that pattern of seizures for them. So we didn't actually need, perhaps, to have electrical activity recorded directly from the brain for that. And that was very important because we'd presumed until then we needed to have electrodes directly in the head. But we can see these remarkable patterns of seizure activity, which are very individual. And we can see these ultradian, so these very short, these day length and very long cycles, and we can use them to forecast the activity. And here's an example of that in use. So here in that top graph, the black lines are showing you here the probability of a seizure. So we're able to say when we think a seizure is going to happen. And you can see once it gets above this red line, we can set that red line so that, for instance, we could say, let's say we want to give you 100% chance that you know when a seizure is going to happen. Then you might get a lot of false alarms, but you might be very sure. But on the other hand, it might suit you better just to be more sure that when you do have one, that's going to be a real one. So you can see this patient, we've got the red triangles here when the seizures are happening, and you can see we've predicted them very accurately. You can see that there are big spikes, though, that don't always have seizures. And that's to be expected. We know that electrically you can see seizures that don't necessarily have any clinical change with them, so that can happen. There's one seizure there, that blue one, which we didn't actually predict quite so well. We're pretty close. But these are relatively early days, and you can see that it's possible, once you've got this information, to make these kind of predictions, which I think is terrifically exciting. Here's another example of these cycles, these multi-day cycles. So you can see here again these swings and peaks in this activity, and you can see as the activity reaches its peak, that's when the seizures are happening. But the interesting thing here is this is heart rate. So this isn't the brain's electrical activity, this is heart rate. So there are features of heart rate variation that seem to tell you what's happening with the brain. So that the heart's not causing these. I mean, some people are having seizures or what look like seizures because their heart's stopping briefly, but this isn't that. This is your heart rate's changing a little bit over time because your brain's changing. So your brain's got nerves connected to the heart, and it's probably affecting how the cycle of your heart activity runs during the course of the day. So this is important too. So maybe, and this might not be true for everyone, but maybe we can use the heart's activity to figure out what the brain's doing, and that will help us with seizure prediction as well. And again, we can do those sorts of graphs where we can tell over what time of day the events are more likely to happen according to their cardiac cycle. So this gets complicated. So that the cardiac cycles shown there, we can see these cardiac cycles, and we can link them to the EEG changes, and we can get these, again, very individual cycles of heart activity out of people's individual ECG traces if we've got them for long enough. And of course now with a lot of wearable things you can extract these heart rhythms from watches and what have you with the resolution that you need to do this. And that's a problem, getting the data out of these things and being able to analyse it and so on. So all of these are very complex challenges still. But you can see, like I showed you for the seizure activity, you can figure out these cycles for individuals, figure out what time of the day, what day of the week, what week of the month, and so on, they're going to be more prone to seizures. And it's not as straightforward as just picking those times and saying that's when they're going to happen. They all interact in a very complex way. But you can get that information out of it. That's some work published by Philippa, who's done so much work in this area in our team, showing you these links between these various cycles. Now, if you can do it with the cardiac cycle, could you do it with other things? Well, maybe you could do it with just a diary. And again, Philippa did this work looking at the diary-based estimates. So this is from the patients in the NeuroVista study and patients using a mobile app. So we had patients using their NeuroVista device, the implanted device, with a diary. And we had those where we had their actual EEG, so we could see what they thought was happening and what was actually happening, and we could compare that. And so here we were trying to figure out if we could figure out what their risk was and how much time they had to spend in high risk if we gave them a warning. Because obviously if you've got a device that's warning you, you don't want the thing to be on all the time. In fact, one of the patients in the NeuroVista study who we did really well with from our point of view, so we very successfully predicted her seizures, she was very unhappy with it because it told her she was having seizures all the time, which turned out to be correct. I mean, she was having hundreds more seizures a day than we thought. But that's not very much use to her. And similarly, if you have a device that tells you on any day you've got a 50-50 chance of having a seizure or more, then that's of no use to you. So you need to get the risks you've got to predict well, and you've got to keep people in as little time as you can. So you want to keep them up on this side of the line here. You want to keep them having little time as you can in little time as you can in high risk, and being pretty accurate with predictions. So ideally you'd be up here, you'd be saying 100% of events are happening in a very tiny proportion of your time. That'd be ideal. And as well, knowing that when you're in low risk is great too. And in fact, a lot of patients found that more useful. So the system gave them a blue light telling when they weren't going to have a seizure. That was actually more useful. So knowing you're not going to have a seizure and you can go about things confidently, that's terrific. So ideally, you'd give them as much time in low risk as you could. and they wouldn't be having seizures then. So that's where we'd like to be. And you can see that using the data from Diaries and so on, the mobile app, the Seizure apps, and those of you who use the app will know there's a toggle on it now so that you can switch it on and get seizure forecasting done just based on your diaries. There are some problems because I showed you earlier that diaries aren't accurate, but if there's enough events, and some people are just better at picking their events than others, it can work very well. So Rachel's done a lot of work on this too with Philippa, looking at these cardiac cycles and figuring out whether we can use combinations of the diary and watches to more accurately forecast seizures, because we can combine the information from the diaries that people collect in their app, and we can use the Fitbit data. We've been working very closely with Fitbit, but we can use information from other devices as well with these systems to help predict when events are going. And so we've been looking at this study that we started a couple of years back now, looking at their seizures and how well we can predict them with these kind of systems to see how accurately we can do it. And as before, we use these cardiac cycles, so we extract the cardiac cycles, we figure out the long and the short cycles within that, and that's shown here. So for this patient, the important cycles, so there's this 24-hour cycle. This patient's got a very good 7-day cycle, one out at about 15 days, and another one out about 33 days. And you see cycles out really long time films. So there's another patient, same thing. You can see the cycles are different for this patient though. It's still that very strong 24-hour one, and we see that a lot, but also one out about 30 days there. And when we looked at this for all of the patients, we found that for those who stuck with it, and here on this graph, so all of these individual lines here represent an individual patient. You can see they're in it for varying periods of time, and the darker shading represents a significant cycle. You can see they're kind of different. You see the very strong cycle here, very dense colour for just about everyone at about a day, and you can see a pretty strong cycle out at 7 days, one at about 30 days, but you can see people have cycles going way out into the distance. They're not usually exactly 7 days, but they're close to it. Here for someone, for instance, their weekly cycle, they've got a fortnightly cycle as well, and they've got a monthly cycle. And we can combine all of that information to give them a pretty good prediction of when seizures are going to happen. So of those who'd had a few seizures, so at this stage when we put this information out, at least 10 of them had seizures that we could lock closely to their cycles. So it's not for everyone at the moment, but you can see it's an area where there's a lot happening and things are improving pretty rapidly. So all of this is great, and the wearable stuff's fantastic, and obviously there are many wearable things coming. There's other kinds of sensors too. I mean, not only is there heart rate, but people are developing things to monitor oxygen and other body functions, and maybe all of that information could be put into these sorts of systems too to help predict when events are happening. But you still got to wear a thing, and there's still a problem of how accurate the information is, and we've seen that it can work very well for some people, but doesn't work very well for others, perhaps because they're not very accurate at picking their seizures. And all of these things, as with the seizure cycles, generally we haven't shown that for everyone that we can pick them yet, but then only a few people have had these devices in. So in the world, there's only a few dozen people who've had events of this kind just recording in. There are more people who've had these more elaborate devices put in which are meant to treat seizures, which are the NeuroPace systems, which involve penetrating electrodes into the brain to deliver a little electric shock to stop a seizure. They don't record continuous EEG activity, but they do record when seizures are happening, so you can get accurate information about the timing of them, which you can also use for these sorts of purposes. But the problem that we had was we had a good system for doing it with a device that we implanted, but it was very invasive to implant, and people who financed these things didn't think that was a goer, and so that company collapsed. We thought until then that we needed to collect information directly from brain to make these predictions, but we've seen that maybe you don't need it direct from brain. If you know when seizures are happening accurately, you can do it just by picking these cycles, but you do need to know accurately when the seizures are actually happening. But as well, you can build on it with heart rate information and perhaps other information that we can get for wearables. So there's a few things there, but having EEG the brain's electrical activity recorded is obviously best. If we've got that, we can see seizures. But it was going to be a tough ask to get anyone to put up the sort of money you need to develop these devices. And remember that developing these devices costs hundreds of millions of dollars. And it's unimaginably complicated. And the only reason I got involved in it was because I didn't know how complicated it was. Otherwise, I never would have done it. So this started a long time ago. So a long time ago, we started looking to see whether we could use a device like this. So this is a bionic ear. And the bionic ear device is something that, you know, we thought was very attractive for this, because there's a system already made which has a source of power and you can get data on and off it. And rather than going into the ear and delivering stimulation to the ear for hearing, we figured we might be able to use it to record the brain's electrical activity. So we modified the systems. And this is a job over a very long period. And so there's a basic sort of cochlear system. That's a pretty old-fashioned behind ear unit that they would wear. But remember, a bionic ear system needs to be listening as well and turning the information to digital signal and sending it back into the nerve to the ear. So it's a bit more complicated. You can see on the bottom right there's some of our early prototype devices. And it's hard to believe that I went around trying to sell this to people in a Tupperware box. You know, people I thought might be interested to give money, and strangely enough, I couldn't get them involved. But we did eventually. And we did a lot of work in sheep. So a lot of sheep have had these devices implanted. The sheep don't have epilepsy, but we figured out how to make the electrodes that we needed, how to implant them, and we figured how to put them in them and send them out to pasture, and demonstrated that we could record their signal over very long distances. So these were out in fields in Werribee outside Melbourne, and we could capture their EEG signal continuously and so on. Turns out sheep butt their heads a lot, which isn't very good if you put electrodes under their scalp. And we ended up with these sorts of systems. So that's one of the implanted systems there at the moment. This coil is how you get power into it. And in the middle there's a magnet. And this sits on the outside of the head, but you'll see some more pictures of that later. So that holds on. But you will have seen people with bionic ears, and maybe people here have them, that clip onto your scalp. So all of the silver part here is under the scalp, and all of this is behind your ear or sticking on your scalp, where it hangs on just with the magnet, and you can take that on and off. But there's a battery in there and a Bluetooth, and that can send data out. And so we developed these so they could be implanted like this under your scalp. And this is our Minder implant. So this is an investigational thing at the moment. So I'm not telling you about anything that you can go out and buy, and all of the results I'll tell you about this are a very preliminary piece of information. So keep that in mind. But you can see that with Cochlear, who build a bionic ear, we were able to get them on board to manufacture these systems for us, and they're a big part of the deal now. So we build these devices and we can put them in just like a Cochlear device. So we make a cut behind your ear, which is about 7 centimetres long under the hairline, and we insert the can that you can see there, and then we can just feed the electrodes through under your scalp across the top of your head, and that takes us about 30 or 40 minutes to do. And then the data that comes out of the behind ear unit is transferred to your mobile phone, and the mobile phone sends it to the cloud, and in the cloud we analyse it. And because you generate huge amounts of EEG data with this, no one's ever going to be able to sit down and look through it all. And again, this was something which hadn't occurred to me, particularly when we did the first study with the Neurovista device. I was at a meeting and someone said, sure, but if you've got a few hundred of these, then the rest of the world's population is going to have to be sitting around computers looking at the screen, figuring out what's going on. And I thought, well, that's true probably, but we hadn't thought that far ahead. But we did need a way of automatically being able to analyse the data coming out of these systems. And so we developed a machine learning based system, which is what we use in our diagnostic service at Seizure, which analyses the data coming out of these things continuously. So data being streamed out of implanted systems or warned systems such as we have is capturing this EEG data and figuring out what's happening, because no one's ever going to be able to sit down and look at these screens of data continuously to find the infrequent events. And remember, the seizures, I mean, this is remarkable, you know, when you record EEG continuously, the actual seizures occupy, you know, 0.001% of people's life. I mean, it's amazing for the disruption they cause, isn't it? But they're a really, really infrequent and rare event, and finding this in the background of a lot of EEG data is a really big technical challenge. But we've got a system which does that. So all this stuff goes to the cloud and we can analyse it. And all of this is work in progress, but it does work, and we can get it. And there's what one of the devices looks like when we've got it in. So you can see the electrodes going across the top of the scalp there. These little contact points, so there's 4 contact points across it, and they go over both sides of the head so that we can see electrical change on both sides of the brain. And people wonder if we've got electrodes only in one part of the brain, one part of the head like that. This is just all under the scalp. So it's not as good as getting direct from brain recordings in terms of getting very high resolution, but it's pretty good because we don't have all of the movement that happens on the scalp and all the other stuff that stops you getting good signal. So this is all under the scalp, and we get pretty good signal. And we have so far been able to see seizures from all sorts of the parts of the brain that we've looked at. So we know that it's possible with these. And here you can see someone, so that's our wound about 10 days after we've done it. And there's someone wearing one of the systems. She's had her hair cut very short for the procedure, which she didn't really need to do, but there you go. And you can see here. Catherine is got the implant. Catherine, so all connected up. So far, so good.
Yes.
Just turn your head a little there to the side so we can see that connection, but that's got the longer cable on it at the moment, but it'll be much easier with a shorter one for you during the day. We're getting nice EEG recording directly off that device there. So that's very exciting, being able to see the EEG come live off someone on the phone like that. And that was our first connection, so that was a great moment, seeing the stuff. And you could actually see seizure activity on that patient. That very first screen, you could see some seizures travelling across, some bursts of little seizure activity. So we can use this. So we do a bit where we compare it to scalp recording. So people come and get some ambulatory monitoring done where we put electrodes on the scalp to make sure that we're recording what we think we're recording. And this is a seizure. So all these green ones are the scalp recording. The blue ones down the bottom here are implanted electrodes. And you can probably appreciate here that you can see the seizure. You can see it on the scalp, but we can see it very nicely in our electrodes here. The red ones here are electrodes we've stuck on the scalp above our implanted electrodes just to compare them. You can see they're a lot noisier. They don't give us the nice clean signal. And this shows you our machine-based learning system. So the green shaded bit is where the machine's detected an event. So all of this stuff will run through, the device will detect it. And we can see these very long patterns of seizure activity once again from the recorded information. And we might be able to see other things as well, like what's happening with the treatment and so on. And we showed with the first couple of patients that we implanted that it's possible to use this information in the same way as I showed you with the fully implanted device, so that we, instead of recording the features, we can record the cycles. The first 2 patients are shown there. We figured out, the first one had a very strong 11-day cycle, the lady Shaw getting connected, another cycle that you can see runs over about a month. And in that month, the seizures are more likely to occur over a particular 1.5 days, just about. But in an ordinary 11 days, there's about a 15-hour period where they're more likely to occur. So we can figure that all out for it. And we were able to generate from that a probability like this. So again, this is like I showed you before, where you can see the probability of seizures. So here we've got a measure not of the electrical activity, but how likely we think seizures are going to be. The coloured lines here for this patient tell us when we've given her about an 80% assurance that it'll be accurate. So it's pretty good. And all of our events we're picking above that time, just about. Here you can see a bit of a blow up of that. So you can see the probability that's crossing that boundary there where we think that there's a higher chance of seizures, and you can see at the peaks of it, the seizures are actually happening, those little red triangles there. So we can actually do that. Still very early days yet. We've only got about 15 people with these devices in at the moment, but it's an area where things are moving pretty quickly. Not as quickly as we'd like, because COVID, of course, was enormously disruptive, and the first patients we implanted are now reaching their 3rd-year anniversary. And we've been able to do very little in the meantime, just because you haven't been able to get people into hospital, you haven't been able to get people come and see you for a start, which is a big problem. But we've turned this into an operation called EpiMinder. So EpiMinder, we hope, will provide these sorts of devices to people to let them manage their lives a bit better. And you can obviously go and have a look at the website there, EpiMinder.com. These aren't things which are available to buy, as I say, or to go out and get at the moment, but hopefully that's not too far away for everyone. It does require a surgery still, And there is this wearable bit. It doesn't have to be worn behind the ear. You can wear it on your collar. We just put a slightly longer cable on it, and there's a device to clip it onto your collar. But they're no more obvious than people's bionic ear are, obviously, because they're exactly the same external hardware as a bionic ear. And some other neurologists say to me, patients won't be interested to wear these. And I said, well, they will, because it'll tell them stuff that they need to know, and they'll want that. Not everyone will want them, but things will improve over time as the devices get smaller and we get better at powering them. But at the moment, we need that battery in there, and we need some way of getting the data out of the system, because the bit that's implanted is all inert. There's no battery in it, so that can last a lifetime. So there's a lot of complexities to it. So we'll complete this study in Australia, and then hopefully we'll take the system onto other studies elsewhere. So that's where we're up to. So you can see there's a lot in there around the patterns of seizure activity, what you can learn by recording things. The brain's electrical activity is best, but you can get a lot of interesting, and perhaps for some people, maybe all you need from heart rate or other measures of the body's activity, which tell you something about what's happening with the brain. You can see how the diagnostic systems for taking this out into people's home, like we do with our ambulatory monitoring systems, are linked to how we need to analyse this data continuously to catch the events that we're interested in, because people often don't know about them. Even those around them don't always know about them. And capturing this information accurately is important for safety, day-to-day life, figuring out whether your treatment's working, and figuring out what's better treatment. So we do need to do this. So it's certainly possible, forecasting's possible. Lots of different methods, and we've used other methods that I haven't told you about today, which are very more complicated and boring, but very accurate to predict seizures, depending on the sort of signal that you get. There are different methods of doing it. And these rhythms of activity seem to be ubiquitous, so everyone has them. Maybe everyone has them anyway. Maybe everyone without epilepsy has them. I don't think we don't know that yet. I mean, people haven't had continuous EEG recorded, but we do know that people who don't have epilepsy also have these same patterns in their heart rate cycles. So it's probable that people are just having these big cycles in their brain's electrical state, and at certain points of it, you're just more vulnerable to seizures. And if you've got an underlying problem that's produces seizures, that's probably when they're going to happen. So that's probably what we're seeing here. The spikes and another thing called high frequency activity that we can measure have a very complex relationship. So sometimes the spiking activity that we see is very closely linked to when seizures happen. Sometimes it's the opposite. Sometimes the seizure activity is completely out of phase with when the electrical spiking activity is happening. And we can use those less invasive systems for this forecasting. And it might be that the heart rate changes are a good surrogate for that. But I think, the forecasting has tremendous capacity to change everything about how we treat epilepsy currently, how you manage your lives, how you take care of people's safety. And that's what we'd like to do. So millions of people involved in all this, and I won't go through them all, but obviously I mentioned Philippa and Dean have been critically important, but lots of international collaborators involved in all of this over a very long time now. And for me, as a neurologist, it's meant spending most of my working time with engineers, which is very different from most neurologists' life, I guess. But being involved with the engineers and seeing the insights that people bring to the management of epilepsy, other than doctors, because doctors we sort of get trained in a particular way of dealing with things, and getting people in who have a different perspective on things is really, really, really important. The NeuroVista guys who were involved in the original study from the States, they're still very closely involved with us as well. They're not involved in the study, but we see them a lot, and it's a very strong community of people working on these seizure production problems worldwide. So thanks for your attention, and happy to take any questions.